Good afternoon. Thank you for attending CXL Forum. My name is Hokyoon Lee, and I am leading System Software team at SK Hynix. Today, I'm going to talking about two topics, HMSDK and CXL Disaggregated memory, to show our visions for memory-centric world. We are facing two big challenges in memory capacity and bandwidth of various workloads, such as in-memory caching, in-memory database, and as well as AI machine learning require more and more memory capacity and bandwidth. However, as the core count of the state-of-the-art CPUs is increasing, but the memory bandwidth per core is slightly decreased. For the memory capacity perspectives, as shown in the right-hand side figure, we cannot make big growths in memory capacity without big changes on memory subsystem. So every software hardware vendors and engineers really wants to solve these limitations. CXL, so previous talk, so Wansub and Gyeongsan already covered the details of the CXL. I'm gonna quickly review the CXL. So CXL as an open standard designed for high-performance computers with the high PCIe-based high-speed interconnection. So we can extend memory bandwidth as well as capacity by installing 6 CXL memory devices or CXL disaggregated memory. It has been 4 years from the first announcement from CXL consortium started. Finally, we can have CXL supported processors such as Sapphire Rapids Gen 1. And for CXL memory, we can have in the near future the memory device module. So for me, I can have because I'm in the memory manufacturer. So when I attended the first CXL educational tutorial at Google San Jose, more than 200 people were participated in there. So CXL consortium explains the CXL 1.1 specification and covered the CXL.cache, .mem, and .io. So at the beginning of the tutorial, the most of the attendees were excited and welcomed the innovation. So, but the end of the .cache session, some of engineers they really enthusiastic for the CXL that got a coherent interconnect, but some of the engineers says, there is some, the coherence logic good, but how can I implement it? And when can it could be possible? So anyhow, we all CPU, accelerator, and memory companies are trying to make it real. Okay, so let's think about CXL opportunities from memory company perspectives. At first, we can expand memory capacity and bandwidth. Second, we can use different types of memory media. Third, we can differentiate the CXL memory controller by adding special features such as computing engine or real data processing engines. And last, memory disaggregation could be realized by using the CXL pooled memory, since the CXL interconnect allows a host to connect to disaggregated memory. In this talk, I will talk the first and the last topics. So for the first, I will explain about the CXL memory expander solution with the HMSDK, and then for the rest, we're going to explain about the CXL pooled memory solutions. Okay, and last year we announced the first CXL memory samples. Our memory has E3.S form factor and its capacity is 96 gigabytes. This CXL memory device supports CXL 2.0 specification and utilizes PCIe Gen 5 by 8 lanes. There are DDR5 DRAM packages inside. We are using the most advanced DRAM technologies, 24 gigabit dies. And for the bandwidth, it has more than 30 gigabytes per second. it depends on the PCIe RAM bandwidth, and also it depends on the DRAM package, DRAM bandwidth. So from now, I'm going to deep dive into CXL memory expansion solution with HMSDK. Our CXL module can be used with the CXL software processor, such as Super Rapid or Genoa. As you may know, the processor supports 8 channels for the conventional DRAM DIMMs, and we can install maximum 4 CXL modules, CXL expanders, to expand memory capacity and bandwidth. With the combination of the DDR5 DIMMs and CXL memories, a single CPU server can have more than 1 terabyte memory capacity and up to 480 gigabyte per second bandwidth. So here is a question. How can we use the CXL memory from programmer's point of view? Although conventional OS provides page placement policy such as Luma interleaving, but it does not fully utilize system memory bandwidth. So we have developed heterogeneous memory software development kit called HMSDK to overcome the limitations. So please keep in mind that it's not the Hynix memory SDK. So with HMSDK, we can enjoy maximum system memory bandwidth. So our HMSDK consists of CXL aware memory allocator and memory placement policy. The memory allocator provides memory APIs, for example, CXL malloc and CXL free to users, and it supports the major programming languages such as C, C++, Java, and Python. For the memory placement policies, HMSDK provides software managed interleaving called bandwidth-aware interleaving mode. HMSDK automatically recognizes the bandwidth ratio among memory NUMA nodes and allocates their data or OS pages following the ratio. If you visit the GitHub website, which I denoted here, we can get the more information from the HMSDK. So one comment, I introduced the HMSDK software managed interleaving, but the next generation CPUs, Granite Rapids and Turing support also hardware managed interleaving, but there is some limitations. All the DMs, all the CXL memories should be installed, all the channels and all the DIMM and CXL memory should be same capacity. So we provide more flexibility mechanisms for the interleaving. Okay, it's not working. Okay. So we have recently released HMSDK version 1.1. The HMSDK supports multiple CXL memory to enhance the bandwidth-aware interleaving mode. We can expand memory capacity and bandwidth as possible as if we can install CXL memory. As I mentioned before, conventional OS NUMA interleaving has performance limitation because the OS has considered the same performance DRAM until now. The OS evenly distributes OS pages across DRAM NUMA. With these conventional mechanisms, when we use DRAM and CXL memory at the same time, the aggregated system memory bandwidth would be limited by the slow CXL memory. So in order to get the max utilization in terms of memory bandwidth, we need to place pages by NUMA bandwidth ratio. So as a performance result, okay, yeah. Okay. As a result, so when we use two CXL memory devices and two DRAM DIMMs, we can achieve by 27% higher memory throughput compared to conventional interleaving. So, okay, for now, we are focusing on two-tier memory management. Manual papers and articles, so companies announces the two-tier memory management schemes such as autonomous tiering from Intel, TPP from Meta, and TMTS from Google. Also SMDK from Samsung, and memory machine from Membergy. So as a HMSDK developer and CXL memory manufacturer, we'd like to provide the kinds of capability. So our current research is mainly focusing on hiding the hot-cold page classification and also page migration. So we have to reduce hot-cold page profiling overhead as well as IPI interprocessor interrupt, TLB shutdown, and page copy overhead during the page migration, so promotion and demotion. So we have planned to release the updated version of the HMSDK at the end of this year. So let's move on to the next topic. I'd like to introduce CXL Disaggregated memory. So before CXL interconnect comes out, the memory is not a part of a composable disaggregated infrastructure. We could make disaggregated memory by using an RDMA technique, right? But I think it is not actual memory because a software stack always intervenes the RDMA access. However, CXL interconnect enables the real disaggregated memory with memory-centric access. It means CPU can directly access to the remote memory with load store instructions. So the CDI can be a complete form of memory-centric system with the CXL-based disaggregated memory. Finally, data center can make disaggregated resource pool for CPUs, GPUs, and even memory to satisfy resource requirements. Yeah, there are several steps for CXL disaggregated memory. The simplest one is a direct connection with a single port CXL memory. And then next step is multi-headed design that supports a limited number of hosts. It depends on the number of ports. And the last step is switch-based memory disaggregation for scalability. In this talk, I'm focusing on the multi-head design, and I'd like to introduce the Niagara, our CXL pooled memory prototype. Yeah, here is our memory-centric system with 4-port CXL pooled memory and 4 servers at the bottom figure. So this is the middle of this figure. We can see the Niagara CXL pooled memory prototype, and my colleague made this hardware also over there. And it is the world's first CXL pooled memory prototype supporting dynamic capacity service. According to CXL 2.0 specification, CXL memory capacity is divided into multiple logical devices. Since each host server must use only the assigned capacity, a server could suffer from underutilization or memory hungry. So our solution, dynamic capacity service, the solution is that changing the assigned capacity dynamically. So actually, it is very simple solution or obvious. So we named the functionality as a dynamic capacity service, and it is much similar with the DCD, dynamic capacity device, of the CXL 3.0 specification. But prior to release the CXL 3.0 hardware, we have checked the feasibility and the benefits of that, its benefits. Okay, so the green box, pooled memory manager, the pooled memory manager exposes entire memory capacity of the pooled memory to each host, then manages available resources and also checks the access permission for each host. Okay, take a look at the features. The Niagara platform supports CXL 2.0 and up to 4 ports. Therefore, we can connect maximum 4 servers to the CXL pooled memory, and the servers can share 512 gigabytes memory resource. The performance in terms of low to user latency and bandwidth is not good, we expected, because it uses FPGA-based prototype. It is FPGA-based prototype. For the future ASIC-based pooled memory, the performance will be better. It should be. So, okay, for use cases, we have categorized the use cases into 2, resource sharing and data sharing. I will explain resource sharing first with dynamic capacity service. So, for example, this slide shows the initial setup, and the 4 hosts fully utilize or fully allocate pages on the pooled memory. As I mentioned before, CXL 2.0 does not support dynamically changing the assigned memory capacity, but we can do, right? So host 2 send a release request to send a release request to pooled memory manager, and then pooled memory manager so they allocates the blue boxes, blue memory sections, and then host 3 sends allocate request to pooled memory manager, and then this our Niagara pooled memory prototype dynamically changes the permission and then eventually allows the memory sections, it means yellow boxes, to access, allows host 3 to access the memory sections, another additional memory sections. So it's more similar, and host 4 release and host 1 allocate. So this is simple figure. Okay, and then software side. Last year, we built up the CXL-based memory-centric system that supports the dynamic capacity service solution, and we have carefully modified the Kubernetes to support multi-container in cluster level. As shown in bottom figure, the Kubernetes master checks the resource availability of our worker node, including CXL pooled memory resource, on placing or removing a part. Then the master makes decision to allocate or deallocate the pooled memory resource for the workers. Based on the master's commands, the worker triggers DCS engine driver inside the kernel to do memory hot plug or unplug by communicating with Niagara through a mailbox interface. So Niagara platform then has responsible for the providing the available memory resource and also checking the access permissions. Okay, evaluation results. As you expected, right? The DCS enabled Kubernetes cluster improves the memory utilization by 35%. Since the worker node 2 has more CPU cores than the node 1, the node 2 needs to more memory capacity when we launch same containers. It follows the same core to memory capacity ratios. So Niagara provides additional memory. So I can say steals memory from the node 1 dynamically, and then the memory utilization could be higher. So you can find out the detailed information from IEEE micro paper we published. So, okay, the next use case, I think, is data sharing. So it is on the developing with member So host 3 writes some data to Niagara. Then multiple hosts can read the written data. The pooled memory manager do not care of any access permission. So software should guarantee the data consistency and coherence. So we are working with the members on the data sharing use case. So you will be able to find out our CXL pooled memory system and see demos at OCP Global Summit, right? This year, October. So I believe some of you will be there, and please visit us. So in addition, we have planned to enhancing the pooled memory prototype Niagara system by adding special features such as memory snapshot and block data management in hardware side. So block data management is a kind of the internal memory copy or move operations. So we are keep developing that kind of features to enhance our systems. Okay, this is my last slide. So we are right now focusing on CXL BME, stands for bandwidth memory expansion. So I already explained about the CXL memory expander. So we also considering the CXL CME, stands for capacity memory with the large capacity memory media. And also we are keep looking at the memory disaggregation. The first step is our system is Niagara, and then we are keep doing to make the memory-centric system work. Okay, thank you for listening.